Let's get into it. Number 10. Lunar Recession. On a clear night in New Mexico, a team at the Apache Point Observatory fires a green laser pulse at the moon. The beam crosses 384,000 kilometers, hits a mirror the size of a suitcase that Apollo 15 astronauts bolted to the regolith in 1971, and bounces back. Round trip takes about 2.5 seconds. Measure that time down to the picosecond, and the data tells you something uncomfortable. The moon is leaving, not fast, 3.8 centimeters per year, roughly the speed a human fingernail grows, but it has been leaving for a very long time, and the evidence is carved into rocks on both worlds. Tidal friction drives the retreat. Earth spins faster than the moon orbits, so the ocean bulge our planet drags up gets pulled slightly ahead of the moon's position. That leading bulge tugs the moon forward, boosts its orbital energy, and pushes it outward. Earth pays the bill. Our rotation slows by about 2.3 milliseconds every century. Days get longer. The moon gets farther away. The trade has been running since the system formed. Now run today's recession rate backward through 4.5 billion years. The moon ends up inside the Earth far too recently to match the giant impact that created it. The rate cannot have been constant. Something changed the tidal coupling across deep time. Ancient tidal rhythmites help fill the gap. These are layered sediment beds left behind by shallow seas that existed 1.5 billion years ago. The layers record a moon that was much closer and an Earth day that lasted only 18 hours. Between those rocks and the modern laser data sits a window from about 600 million to 2 billion years ago, where the tidal record goes nearly blank. Not enough preserved geology, not enough data points. Continental positions, ocean basin shapes, and resonance effects in ancient seas all shifted the friction over geological time. Models that include those variables can reproduce the sediment record without breaking the physics, but the window stays murky. The moon's slow departure is one of the most precisely measured phenomena in all of science, and yet the middle chapters of the story remain mostly unwritten. For the Artemis crew, the recession is not a metaphor. The moon they orbit sits 3.8 centimeters farther from Earth than it did last year. In roughly 600 million years, it will be too distant to produce total solar eclipses. The system is still running down, one laser pulse at a time. Number 9. The Two-Faced Moon. When Apollo 8 swung behind the far side in December 1968, the crew expected something familiar. What Frank Borman, Jim Lovell, and William Anders saw instead looked like a different world entirely. No broad dark plains, no smooth volcanic basins, just a battered, cratered highland stretching in every direction. Soviet probes had sent back blurry far-side images as early as 1959, but the Apollo 8 crew were the first humans to see the contrast with their own eyes. Near side, smooth and dark. Far side, rough and pale. Same body, two completely different faces. The numbers sharpen the mystery. Dark volcanic plains called Maria cover roughly 31% of the near-side hemisphere. The far side has almost none. Data from NASA's Grail mission, led by geophysicist Maria Zuber at MIT, confirmed the far side crust average is about 20 kilometers thicker than the near side. That extra rock acted like a lid, choking off the volcanic plumbing that could have flooded the lowlands with lava. But why would one hemisphere grow a thicker crust than the other? The leading explanation traces back to the South Pole Aitken Basin impact. That ancient collision, one of the largest in solar system history, may have redistributed heat-producing radioactive elements like thorium and potassium toward the near side. More radioactive fuel meant a hotter mantle. A hotter mantle meant more volcanic eruptions, more resurfacing, more of the dark, smooth Maria we see tonight. In 2024, China's Chang'e 6 returned the first ever rock samples from the far side. Analysis by teams at the Chinese Academy of Sciences confirmed what orbital data had suggested. The far side mantle is cooler. It is also drier, with less water locked into the mineral structures of its basalts. A dry mantle melts less readily and erupts less often. Earth's own gravitational pull adds another factor. Tidal deformation keeps the near side flexing and warm deep down, while the far side sits comparatively rigid. Some models now suggest the asymmetry locked in during the first 100 million years after formation, while a global magma ocean was still crystallizing. Dense minerals sank unevenly, radioactive elements concentrated on one hemisphere. Other researchers argue the South Pole Aitken impact reset the thermal budget of the entire crust so thoroughly that the imbalance became permanent. Either way, the two-faced moon is not a surface feature. It reaches all the way down to the core. Number 8. Lunar swirls. Through a telescope, the feature called Rainer Gamma looks like a broad white brushstroke laid across dark basalt in Oceanus Procellarum. No elevation change, no crater rim, no shadow, just a bright pattern painted flat on the ground, as if someone spilled cream across wet asphalt. Dozens of similar swirls appear across both hemispheres. They have puzzled planetary scientists since high-resolution photographs arrived in the 1960s, and they remain one of the most visually striking unsolved problems on the moon. Every known swirl sits directly above a localized magnetic anomaly. The moon has no global magnetic field, has not had one for at least 1 billion years. Yet these small crustal patches carry magnetic signatures strong enough to measure from orbit. One widely cited explanation, developed in part by researchers at Johns Hopkins Applied Physics Laboratory, proposes that the magnetic patches act as miniature shields. Solar wind ions that would normally darken the surface through space weathering get deflected around the magnetic bubble. The ground inside stays bright. Everything outside weathers and darkens. The swirl is the protected zone. Other explanations compete. Subsurface lava tubes or cooling magma bodies may have locked in magnetic signatures while the moon's ancient dynamo was still active. Cometary impacts could have exposed fresh material or deposited magnetized debris. Electrostatic dust sorting, where the magnetic field physically separates fine bright grains from dark ones, could explain some of the sharper patterns. None of these models accounts for every swirl. The shield theory fits Rainer Gamma well, but struggles with smaller, fainter examples near large impact basins. The cometary model explains some antipodal swirls, but not isolated ones. Recent data from the Lunar Reconnaissance Orbiter shows swirl regions reflect light differently depending on viewing angle. That points to physical differences in grain size or compaction, not just albedo. If the bright patches preserve the original unweathered lunar surface, they are windows into what the entire moon looked like before billions of years of particle bombardment. There is also an engineering dimension. If localized magnetic fields can deflect charged particles on an airless world, the same principle might be engineered into shielding for future habitats. The swirls may turn out to be more useful than beautiful. Number 7. Mascons. In 1968, a spacecraft dipped where it should not have dipped. Lunar Orbiter was sailing over one of the great near-side basins when tracking stations on Earth watched the telemetry shift. The craft dropped altitude, accelerated, and then climbed back to its predicted path. Nobody scheduled that maneuver. Paul Muller and William Sjogren at the Jet Propulsion Laboratory dug into the tracking data and found the cause. Dense material hidden beneath the basin floor was pulling the spacecraft downward. They named the phenomenon mass concentrations, Mascons. The anomalies mattered immediately. During Apollo, the mission planners had to build Mascon corrections into every lunar orbit or risk navigation errors during critical descent burns. Some of these gravitational lumps produce acceleration strong enough to measurably alter a spacecraft trajectory in minutes. fly over Imbrium or Serenitatis without accounting for the tug and the orbit changes, whether the crew wants it to or not. For decades, nobody could agree on what the Mascons actually were. Dense lava fills from ancient volcanic floods. Upwelled mantle rock pushed toward the surface by a rebounding crater floor. The argument ran for 40 years. NASA's Grail mission settled it. Maria Zuber's twin spacecraft Ebb and Flow orbited just 55 kilometers above the surface and measured gravity variations to 1 part in 100 billion. At that resolution, the moon became nearly transparent. A massive asteroid excavates a deep basin and thins the crust. The hot mantle rebounds upward, pushing dense material closer to the surface. Millions of years later, iron-rich basaltic lava floods the lowland and adds another dense cap on top. The cooling crust locks the whole stack in place. A bullseye gravity signature, high in the center, ringed by a low-gravity moat, frozen for over 3 billion years. One surprise from Grail was how perfectly preserved these structures are. Plate tectonics and erosion would erase them on Earth within a few 100 million years. On the moon, they survive untouched, a fossil record of impact physics that exists nowhere else in the solar system. Another surprise was the far side. Over there, the same scale impacts did not trigger volcanic flooding because the thicker crust blocked the magma. Those basins carry negative gravity anomalies instead. Empty bowls rather than dense fills. The same type of collision produced opposite outcomes on 2 sides of one world. Number 6. The Lost Magnetic Field. Pick up an Apollo lunar sample and run it through a magnetometer. Several of those rocks carry paleomagnetic signatures suggesting the moon once generated a field nearly as strong as Earth's current one. That should not be possible. The moon is small. Its metallic core is tiny, roughly 350 kilometers in radius. Driving a dynamo that powerful requires enormous energy and vigorous liquid convection. The moon does not have the obvious machinery for either. Early in the system's history, the moon sat much closer to Earth. Gravitational interactions at that range would have caused intense tidal flexing, enough to stir a liquid core and sustain convection. Another candidate mechanism is mantle precession, a wobble in the spin axis that sloshes core fluid like water in a tilted bowl. Models by researchers at UC Santa Cruz and MIT show both drivers could have sustained a dynamo for hundreds of millions of years. Then the field collapsed. Somewhere between 1.5 and 2 billion years ago, the core cooled past a threshold and convection weakened until the dynamo shut down. Without a global magnetic shield, the solar wind began hitting the surface directly. Charged particles darkened the regolith, stripped volatile elements, and implanted helium-3, hydrogen, and noble gases into the top few meters of soil. That bombardment has continued uninterrupted for over 1 billion years. A 2026 study covered by PBS Nova added a significant complication. The strong magnetic signatures in Apollo rocks may not represent a steady global field at all. Those particular samples came from titanium-rich mare basalts that formed during specific volcanic episodes. When dense titanium-bearing minerals sank toward the core mantle boundary, they may have triggered brief, intense bursts of convection. Under this model, the field did not hold steady for 1 billion years and then go dark. It flickered, brief spikes of strong magnetism separated by long, quiet gaps. If the flickering model holds, then the surface experienced uneven magnetic protection across geological time. Regions shielded during an active spike would have retained more volatile elements. Regions exposed during dark intervals would be stripped and darkened differently. That patchwork may connect to the lunar swirls. Some of those localized magnetic anomalies could be remnants of the final flickers, frozen into cooling lava just before the dynamo went silent for good. For the Artemis crew, the lost field has a practical consequence. The soil under their boots has soaked in unshielded cosmic radiation for longer than complex life has existed on Earth. Number 5. Transient lunar phenomena. On the night of April 19, 1787, Sir William Herschel pointed his telescope at the unlit portion of the moon and recorded a glow, reddish, faint, lasting several minutes. He logged it carefully. Centuries later, observers are still logging events like it. Scientists call them transient lunar phenomena, TLP for short. Brief brightenings, color shifts, hazy patches that appear over specific craters and then vanish before anyone can get a second telescope on them. The catalog spans hundreds of years and the reliability of the reports varies enormously. Some TLP have clean explanations. Meteoroids strike the airless surface at speeds above 70,000 kilometers per hour and produce brief, brilliant flashes as kinetic energy converts to light. The European Space Agency's Nelly-Yoda telescope on Crete has confirmed that small impacts like these happen several times every hour across the entire lunar disk. Those are solved. The longer events are the problem. Observers have described reddish glows and slow color changes in craters like Aristarchus and Alphonsus that last minutes or even hours. Aristarchus alone accounts for over 200 reported TLP since systematic records began. That concentration is not random. The Aristarchus Plateau sits on a volcanic dome laced with sinuous rills and fractures. It is one of the brightest spots on the entire near side. Lunar Prospector detected radon gas emissions near Aristarchus during its orbital survey in the late 1990s. Radon is a decay product of uranium in subsurface rock. Detecting it above the surface means gas is escaping through cracks in the crust. Some researchers model scenarios where tidal stress from Earth periodically opens microfractures and allows trapped gas to vent in short bursts. The gas interacts with solar radiation or charged particles and produces a faint glow that lasts until the fracture closes. If that mechanism is real, then TLP should correlate with the moon's orbital position. Some statistical analyses of historical records show a weak correlation with perigee when tidal forces peak. Others find no clear pattern. The dataset is messy, spanning centuries of uneven observer skill and wildly different equipment. Electrostatic effects offer a parallel explanation. Solar wind charges the surface. Fine dust particles levitate in the resulting electric field. Along the terminator, where sunrise sweeps across the landscape, cascading dust motion could scatter sunlight in unexpected ways. Piezoelectric effects in stressed rock add another possibility. Tidal forces squeeze certain minerals and generate tiny electrical discharges. TLP are brief, unpredictable, and nearly impossible to confirm with modern instruments before they disappear. But they keep being reported, and some have been observed independently from multiple stations on the same night. Those are difficult to dismiss as atmospheric distortion. Something is happening on that surface, intermittently and without warning. The crust beneath the regolith is not as quiet as it looks. Number 4. The moon goo. When Grail and the Lunar Reconnaissance Orbiter measured how the moon flexes under tidal pull from Earth and the Sun, the numbers came back wrong. Not dramatically wrong, slightly wrong. The moon was bending more than a completely solid body should. The best fit required inserting a layer at the base of the mantle that is softer and less viscous than the rock above or below it. Researchers publishing in AGU Advances called it a low-velocity zone, a region where seismic waves would slow because the material is either partially molten or mechanically weak. The press called it moon goo. The leading compositional candidate is ilmenite, a dense mineral rich in titanium and iron that melts at lower temperatures than surrounding silicates. During the moon's early history, when a global magma ocean was crystallizing and overturning, dense ilmenite bearing cumulates sank toward the core mantle boundary. If pockets of that material remain warm enough to stay soft, they would explain the excess tidal flex. A partially molten layer at depth changes several things at once. It alters how the moon dissipates tidal energy. It changes how heat escapes from the core. It may explain why certain deep moonquakes cluster at specific depths. And it contradicts the standard model of a body that formed hot, differentiated quickly, and then cooled monotonically for 4 billion years. A persistent warm layer does not fit a simple cooling curve. Not every researcher accepts the melt interpretation. Some argue that advanced rheological models, which describe how solid rock deforms under repeated cyclic stress, can reproduce the observed tidal behavior without any liquid at all. The debate sits at the boundary of mineral physics, and the pressures involved are difficult to replicate in any laboratory. If the goo is real, then something has kept it from solidifying. Candidates include residual tidal heating from earlier epochs when the orbit was more eccentric, and radiogenic decay from long-lived isotopes of uranium, thorium, and potassium that may have sunk with the ilmenite during mantle overturn. Possibly both. Whatever the answer, the moon's deepest interior may still be evolving. Moonquakes, tidal deformation, and even the gas emissions observed at Aristarchus could all trace back to processes in that hidden warm layer. The next generation of seismometers will need to listen carefully. Number 3. Water ice. In October 2009, NASA deliberately crashed a spent Centaur rocket stage into the permanently shadowed floor of Cobedeus crater near the lunar South Pole. The L-Cross spacecraft trailing behind flew through the debris plume and analyzed it with spectrometers. Project scientist Anthony Colapret at Ames Research Center confirmed what the data showed. Water ice. Mixed in with mercury, hydrogen sulfide, and other volatiles that had no business existing on a world the textbooks had labeled bone dry for decades. The discovery did not come from nowhere. Orbital neutron detectors on Lunar Prospector had flagged hydrogen enrichment near the poles back in 1998. India's Chandrayaan-1 confirmed hydroxyl and water molecules on the surface in 2009 using the Moon Mineralogy Mapper instrument built at JPL. But LCROSS turned a hint into a confirmed detection. Water was physically present in the regolith of a permanently shadowed crater. The mechanism is straightforward. Crater floors near the poles that never receive direct sunlight sit below -160 degrees Celsius. At those temperatures, any water molecule that wanders in, from a cometary impact, from volcanic outgassing, from solar wind hydrogen reacting with oxygen in the soil, freezes on contact and stays. Some of these cold traps have been collecting molecules for over 3 billion years. The distribution is the puzzle. Some shadowed craters are loaded with hydrogen signatures. Others that should be equally cold are nearly empty. Recent work shows the answer partly lies in time. The moon's axial tilt has shifted across geological history. Not all craters have been in permanent shadow for the same duration. Those that entered darkness 3 billion years ago accumulated far more ice than craters that became cold traps only a few 100 million years back. Micrometeorite gardening complicates the picture further. Constant tiny impacts churn the upper soil, breaking up shallow ice deposits and mixing them deeper into the regolith. The result is a patchy, unpredictable inventory that orbital instruments can detect but cannot accurately measure. 3 different deposit types tell 3 different origin stories. Thin surface frost visible to infrared sensors likely forms molecule by molecule as solar wind. Hydrogen hits oxygen-bearing minerals. Buried chunks mixed into the soil at depth could be remnants of ancient comet deliveries or volcanic eruptions that vented water vapor from the deep interior. And if thick sheets of relatively pure ice exist in the coldest, deepest shadows, they would require either a single massive delivery event or sustained volcanic outgassing over millions of years. Which source dominates determines how much total ice the moon holds. Solar wind production is slow, but essentially perpetual. Cometary delivery depends on the collision history of the inner solar system. Volcanic contribution depends on how long the moon stayed geologically active. Artemis missions to the South Pole will carry drills and spectrometers designed to settle the question. But reaching the ice means landing in perpetual darkness and operating on battery power alone. The resource is protected by the same brutal conditions that make it worth reaching. Number 2. Moonquakes. Between 1969 and 1977, 4 seismometer stations placed by Apollo astronauts recorded thousands of seismic events on the moon. Scientists at the time sorted them into 4 categories. Deep moonquakes originating hundreds of kilometers below the surface repeat on a predictable schedule tied to tidal forces from Earth. Thermal moonquakes come from the crust expanding and contracting as the surface swings between 250 degrees Fahrenheit in daylight and minus 280 at night. Meteoroid impacts register as sharp spikes whenever a rock hits the ground. Then there are the shallow ones. Shallow moonquakes originate in the upper 20 to 30 kilometers of the crust. They can reach 5.5 on the Richter scale. On Earth, a quake that strong cracks, plaster, and shifts furniture. On the moon, where fractured dry rock transmits vibrations with almost no damping, the shaking can ring for over 10 minutes. Some Apollo recordings captured reverberations lasting more than an hour. The ground does not absorb energy the way wet, layered terrestrial rock does. It rings. The cause stayed unclear for decades. Then high-resolution cameras on the Lunar Reconnaissance Orbiter revealed something across the entire surface. Lobat scarps. Stair-step cliffs where one slab of crust has been thrust over another, some only a few meters tall but running for kilometers. Many of these scarps are less than 100 million years old. Some cut across terrain that formed only tens of millions of years ago. The moon is shrinking. As its interior cools, the entire body contracts. Over the last several 100 million years, it has lost roughly 50 meters in diameter. On a body 3,400 kilometers wide, that sounds trivial. But the crust is brittle. It has no tectonic plates to absorb the strain. Instead, it cracks, and when it cracks, shallow moonquakes follow. Researchers have matched specific clusters of Apollo-era quakes to individual lobate scarps. The faults are not relics, they are active. In 2024, a team applied modern denoising algorithms to long-archived Apollo seismic tapes and uncovered 22,000 previously hidden events. That nearly tripled the total catalog. The moon is far more seismically active than the original Apollo data suggested. Several of these young scarps have been found near the lunar South Pole, precisely where Artemis planners intend to build long-term infrastructure. The compressive stress from shrinkage does not distribute evenly. It concentrates along certain latitudes and longitudes depending on the cooling pattern and existing weaknesses in the crust. Mapping those stress zones is now a safety priority for landing site selection. Prolonged shaking also interacts with regolith. On steep crater walls or near scarps, loose soil could flow downhill in slow-motion landslides, burying equipment or destabilizing foundations. 4 Apollo stations running for 8 years captured only a sliver of the full seismic picture. A global network is needed. Until then, the 22,000 newly found quakes deliver a clear warning. The ground beneath any future lunar base is still moving. Number 1. Lunar dust. Harrison Schmitt climbed back into the Apollo 17 lunar module after his last surface walk, pulled off his helmet, and within minutes started sneezing. His eyes watered. His throat burned. He called it lunar hay fever. The symptoms eased within a day. But Schmidt's exposure lasted only hours. No human being has ever breathed lunar dust for a week straight. Nobody knows what that would do. The physics come first. Lunar regolith is not like any dust on Earth. Wind and water round terrestrial particles over time. On the Moon there is no wind and no water. The dust is created by billions of years of meteoroid impacts pulverizing rock into grains finer than talcum powder, each one jagged, glassy, and sharp at the microscopic level. Those edges abrade spacesuit fabric, scratch helmet visors, jam zipper teeth, and grind into mechanical joints. Apollo crews reported suit degradation after just a few walks. Then the chemistry. Without an atmosphere, the grains are continuously bombarded by solar radiation and cosmic rays. That bombardment strips electrons and leaves the particle surfaces chemically reactive. Laboratory studies at Stony Brook University using lunar simulants showed that fresh reactive dust generates free radicals on contact with moist tissue. Free radicals drive oxidative stress, inflammation, and DNA damage. The real dust, never weathered by air or water, is expected to be more reactive than any simulant. Then the electricity. Solar wind and ultraviolet light give lunar dust a persistent electrostatic charge. Charged particles cling to every surface they touch. They resist brushing. They resist blowing. They resist vacuuming. Apollo astronauts tried every removal method available in the cabin and failed. The dust worked into seams, connectors, optical instruments, and air filtration systems. Once it arrived, it stayed. The charge does more than make particles sticky. On the sunlit hemisphere, ultraviolet radiation knocks electrons out of surface grains, leaving them positively charged. Across the terminator on the night side, electrons accumulate and grains go negative. The voltage gradient at the boundary can launch fine particles off the ground entirely. This process, called electrostatic levitation, may explain a phenomenon Apollo astronauts reported from lunar orbit: a faint glow along the horizon just before orbital sunrise. Scientists believe that glow was sunlight scattering off a thin suspended cloud of dust, hovering meters to possibly kilometers above the surface. The finest particles, those smaller than 2.5 micrometers, are the medical concern. They penetrate deep into lung tissue. Animal studies have found lunar simulant causes inflammation in pulmonary cells and may damage neurons. For the brief Apollo excursions, the exposure was tolerable. For Artemis crews spending weeks or months on the surface, it becomes a defining operational threat. Current mitigation plans include electrostatic cleaning devices, suit designs with rear entry hatches that never pass through the pressurized habitat, and surface coatings engineered to repel charged particles. None of these systems have been tested with actual lunar regolith in actual lunar conditions. The dust does not stay in its own category. It coats solar panels and cuts power generation. It contaminates ice samples pulled from shadowed craters. It embeds in instrument optics and degrades every measurement. It grinds against every seal on every airlock after every surface walk. Every other mystery on this list interacts with dust in some way. It is not the most dramatic hazard the Artemis crew will face. It is the most relentless.